Welcome to ECE 302. This is lecture 2.5 on independence. I am Professor Stanley Chan. Today we're going to learn about a very important concept in modern data analysis and machine learning. This notion of independence plays an extremely important role because if the variables in your data set are dependent, then the analysis will be extremely difficult. However, if the variables in your data set they are independent, your analysis will be substantially simplified. However, the notion of independence could be abstract, and many students find this independence argument to be not as easy. The reason is that when we look at two events, we have a tendency to just quickly tell whether one event is influencing the other event. However, this notion of influence could be somehow misleading in the context of independence. We are going to understand what do we really mean by influence, what do we really mean by independence. So here is the outline of today's lecture. We will talk about the meaning of independence, and I'm going to show you examples. By the end of this lecture, you will be able to distinguish between what is independence and what is disjoint. You will be able to tell whether two events are independent or not, and you will be able to argue from a more mathematical way than just hand-waving arguments by saying that two events are independent or not. And this will make you substantially different than someone who do not know independence. So to start with, let me show you an extremely simple example where anyone can tell whether the following two events are independent or not. These two events are that you throw a dice twice and then you get the first number. The first number is 3, and then you get a second number. The second number is 4. We ask whether these two events, A and B, are independent or not. Now, these two events should be very easy to tell because the first event has absolutely nothing to do with the second event. Or if you prefer to argue from this influence point of view, having the first event will have no influence to having the second event, or vice versa, having the second event has no influence to the first event. And so we can argue that, well, then these two events, they are independent from this hand-waving argument of influence. So everyone feels comfortable, right? Okay, now let us consider a slightly more difficult case where the first dice is giving you 1, and then the event B is that the sum is 7. Now, this is not quite the same as the previous example in that in the previous example, it's crystal clear that the two events, they are not influencing each other. Here, event A has definitely some influence to event B because if you get event A, then getting the first dice being 1, you do have limitation on what options you can get for the second dice if event B says that the sum is 7. Vice versa, if you know that the sum is 7, there are really limited options that for you to get the first dice to be 1. So if you think about it from this influence point of view, A is influencing B and B is influencing A. So we do have a natural guess that these two events, they are dependent. So we are going to look at this problem more carefully in a few minutes. Okay, but to really address this problem, we need to understand the difference between our hand-waving argument of using influence versus a more mathematical principle using this independence. And a very key difference is that independence is talking about the probability. It's not talking about the relationship between two events. It's talking about the probability of two events. And therefore, whenever we want to talk about independence, we need to look at this thing from the probability point of view. So without further ado, let us introduce this definition of independence. We say that two events, A and B, are statistically independent when the following definition applies. Here you have event A and B, and then you're considering the intersection of A and B. If this intersection of the events can give you the product of event A times event B, then we say that the two events, they are independent. Now, you may try to recall the axioms. Okay, so the axiom, it says that the union of A and B is going to give you A plus B when A and B are disjoint. Okay, and here independence is applied to the intersection of A and B, and here you will get the product. And this is not limited to just disjoint or sets like that. In fact, disjoint and independent, they are just two completely different concepts. What is disjoint? Disjoint means that event A intersect with event B is empty. Independent says the probability of A intersect B will equal to the probability of A times the probability of B. Clearly, these two are completely two different definitions. Now, if you have two events being disjoint, then the probability of A intersect B will just be the probability of the empty set that will give you 0. If you have two events being independent, having this being 0 will force either probability of A equals to 0 or probability of B equals to 0, meaning that either A is empty set or B is an empty set. That is not the definition of independence. Okay, if this is being 0, meaning that the two events, they are disjoint, then if they are also independent, then the two events, one of them has to be an empty set. So the bottom line is that disjoint does not imply independence, and being independent also does not imply that being disjoint. So these two are just completely different concepts. So how do we understand pictorially the difference between this disjoint and independent? Well, remember that disjoint is that you have two sets that they are not overlapping with each other. How about independence? To understand this independence, we can use the following notion of conditional probability. Recall the definition of a conditional probability of A given B. This is the ratio of the A intersect B divided by B. Okay, so if A and B are independent, then the intersection of A and B will give you this product. And so we can write down the definition of the conditional probability, which is this ratio. And by independence, we can have the following equality. And so in the numerator, you have PA times PB. And clearly, you have these two terms that can be cancelled. And therefore, you will left with the conditional probability of A given B will equal to the probability of A, which is the unconditioned probability. So here, you can see what we really mean by independence. Suppose B has happened. Then the probability of getting an A is not influenced by this presence or absence of B. Okay, so that is the meaning of this conditional probability. Now we have to be very clear that independence is talking about the probability, not the bare influence between two events. Certainly event B will have influence to A or vice versa. However, if the two events stay independent, the probability of A given B is unchanged. It will be the same as the probability of getting an A. And here is a very nice pictorial interpretation of the independence. When you have this A intersect B, A given B, essentially what you are looking at is that you have this sample space, and then you have an event A, and then you have an event B. And now you are looking at the intersection of A given B out of this B. So let's say this is your B. So this is your ratio of probability of A given B. This is the red divided by the orange. Okay, and then what is this unconditioned probability of A? This unconditioned probability of A says that I am going to look at this entire thing. This is my A, this is my A, and then I am going to look at this ratio compared to this entire sample space. So the probability of A is the ratio between this blue divided by the gray. And so when you say that the two events are independent, then you're putting a geometric interpretation that this ratio are being the same. That is very, very different than saying that the two events, they are disjoint. The disjoint would just say that the two sets, they are not overlapping. Independent says that this ratio of the red and the orange versus the blue and the gray, they remain the same. Okay, again, I want to emphasize that independence is the independence of the probabilities. Okay, so you're always talking about the independence using the notion of probabilities, not the simple influence or not. So let's go back to the examples that we have seen before, and then we are going to look at more examples. This is the first example we have seen. Suppose the first dice is 3, the second dice is 4. We ask whether the two events are independent or not. And we can show that probability of A is 1 over 6. Probability of B is also 1 over 6. And then the probability of A intercept B, that is the probability of getting 3 and 4. This is 1 over 36. Okay, and then you can see that that is the probability of A given B is the same as the probability of A times the probability of B, and therefore the two events, they are independent. Now, let's move on to the more difficult case. Suppose that you throw the dice twice, and then the first dice is giving you 1, and then the second dice is giving you 7. Now the sum is 7, okay? And we ask whether the two events, they're independent or not. So what is the probability of A? The probability of A is 1 over 6, that's clear. The probability of B is, well, we need to enumerate all the possible cases getting 7. So that will be a 1, 6, 2, 5, 3, 4, 4, 3, 5, 2, and 6, 1. So in order to get to 7, I have 6 out of 36 options. So that will give me 1 over 6. And then what is the intersection of A intercept B? That has to be this case, because the first dice is 1, the second dice has to be 6 in order to give you 7. And so this is 1 over 36. And so now you can see that the this equality of A intercept B will actually equal to the product of A and B. And so Are they independent? Yes, they are actually independent. Okay, why is this true? Well, you can again go back to the diagram. You can draw the diagram and showing that here you have 36 options. Okay, and among these 36 options, you can choose 1, 6, and then 2, 5, 5, 2, 3, 4, and so on. So these are all the possible cases that you can get from this event B. So these are event B, okay? And now you are getting the event A. This event A is here. Okay, so this is event A. And this event, okay, so this event A it also includes all the cases here, okay, because the first dice is all 1, and then the second dice I don't need to consider, so that's event A. And then here, this dot would be intersection of A and B. And so now you can calculate what is the ratio. Well, the ratio between A intersect B divided by B. So here I'm looking at the probability of A given B. That is the ratio of probability of A intersect B divided by the probability of B. That is the orange dot, this dot, divided by all these green areas, and so that will give you 1/6. And then you can also show what is the ratio between all these yellow, okay, so you have this yellow over the entire sample space. This is your omega. This is the probability of A, and it happens to be 1/6 as well. And because this ratio matches, and therefore you conclude that these two events, they are independent. Now, let us change the scenario to that the sum of the two numbers is 8. Okay, and so now we can see whether the two events, they are independent or not. Now, if you stick to the hand-waving argument by saying that whether A is influencing B or B is influencing A, that would be extremely difficult. Okay, and because in the previous case, when you have a sum equals to 7, we show that it is independent. Okay, but in this case, when the sum equals to 8, will the same argument still work? Well, we can actually look at the calculation. Okay, so what is the probability of A? The probability of A is 1/6. The probability of B is we need to calculate all the possible cases. So in order to get 8, you have to get 6, 2, 5, 3, 4, 4, 3, 5, and then 2, 6. So you have 5/36 options. And then the probability of A intersect B, this is what? Well, this is the probability of an empty set, because it is impossible to get 1 and sum equals to 8. So you get 0. All right, so are they independent or not? No, because the product of A and B is not equal to the intersection. So they are dependent. Now you can see that why this hand-waving argument does not work. The hand-waving argument, it seems to work here, but it does not work in the previous example. Okay, the hand-waving argument saying that A is influencing B, B is influencing A, that kind of argument does not work. But if you follow our definition, it actually works. Now, if you want to draw the diagram, that will also tell you why. So let's say we have 36 numbers, okay? And then what would be the event B? The event B will be 2, 5. So 2, 5, and then 2, 6. Okay, 2, 6, and then 5, 3, 5, 4, 4, 5, 3, and 6, 2. So this is your event B. And then where is your event A? The event A is here. Okay, so here is your event A. Now you ask whether there is an overlap or not. There is no overlap, and so the A-intercept probability of A-intercept B, this is 0, okay? And then now you can also calculate this probability of A, which is this area, this is 1 over 6. Probability of B is this area, which is 5 over 36. Okay, and you can see that these two ratios, A times B, just does not match with the intersection of B. And you can also show that this A given B, this is 0, okay? Because given that B has happened, A has absolutely no chance of happening. Now, how about we also change the problem to this one? Suppose the first dice is 2. Would this ever change our situation? So you can actually go back to the diagram before. So here you have 6 numbers, okay? And then we know that the event B will be here. This is event B. And then the first dice is 2, so you have this. Okay, so now are you overlapping? Well, you do have overlap. Okay, and we can calculate the probability of A given B, which is the ratio of A-intercept B divided by the probability of B. This is going to be 1 over 36, because this is the situation, right? And then you look at the event B. Event B, you contain these 5, so you have 5 over 36. So this will give you 1 over 5. And then you can also calculate the probability of A. The probability of A is here. This is 1 over 6. Okay, and you can see that these two, they are not the same. Okay, and so are they independent? Well, no, they are dependent. If you want to follow the precise definition of A-intercept B and then probability of A, probability of B, you can also show that the probability of A-intercept B, this is 1 over 36. Probability of A is 1 over 6. Probability of B is 5 over 36. Okay, and therefore the product of these two numbers is not the same as this number, so they are dependent. So here is just some additional notes that you can read. And then let us work on example number 4. Here we have event A where the maximum is 2, and then B that the minimum is 2. So we are going to draw a diagram that contains 6 rows and 6 columns. So this is the first dice, and then here is the second dice. So you want the maximum to be 2, and therefore we can ask what would be the coverage by the event A. So you want the bigger one to be 2, right? So suppose you pick a 1 and 1 here. Well, the bigger one, of course, is 1. Okay, but now once you pick the bigger one to be, we have 1 and 2, then certainly this is involved. Okay, so this is okay. All right, and then okay, so the bigger one is 2. Okay, and then this one is also okay. Now this one is not okay because why? Because when you have 1 and 3, the bigger one will be 3. So this is not included. And so here is also included. So this is event A. Okay, event A will contain all these numbers. How about event B? The minimum is 2, and so you can see that event B is here. Okay, so these are event B. Okay, this is B. And we ask, would A and B be independent or not? Well, so we can calculate the probability of A, probability of B, and probability of A-intercept B. Okay, so probability of A is 3 over 36. Probability of B will be 9 over 36. And then probability of A intercept B will be 1 over 36. So this is about 1 over 4, and here is 1 over 12. And you can clearly see that the product of these two does not equal to this number. So this is dependent. So finally, let me comment on why do we want to study independence. Suppose you are in a room and there are many molecules in this room. And now you want to study the statistical properties of these molecules. It will be easier or harder to study this case or that case. Now let's look. If all these molecules, they are moving up and down, left and right independently, then what I need to do is to just pick any one of those and then just study them, assuming that they have the same randomness. Okay, and because they're independent, studying everyone together is the same as just studying one. If they're dependent, then I'm sorry, there is no simpler way, but you need to look at the correlation between all these molecules together. And so in terms of modern data analysis, if you have all the data, they are independent, then you can just look at one of those and talk about its statistical properties. And then just multiply by the number of molecules in your data set. That will give you a description. But if all these data points, they are dependent, then you need to look at their correlations. Then you need to look at the relationship between all these molecules. It could be that this molecule is very far away from that one, and so they have less dependency. And then these two, they're close together, they have a higher dependency. Then analyzing all these data points together, it will become a lot harder. So we will use this notion of independence often when we go to the topic on multiple random variables. So just bear in mind that this independence is important. It can only be taught from this definition of the probability. It has nothing to do with the influence or not, this kind of hand-waving arguments. And you need to follow this mathematical principle because we are looking at the probability. All right, so that is the end of this lecture. I hope you have found this meaningful and useful to your study. And if you have any question, please feel free to send us an email or post your question on our class piazza. Thank you.